In this section, I wanted to do a couple examples of how to solve an equation using the quadratic formula, even though it's not in quadratic form to begin with. Like in the last couple videos, I did a lot of examples of solving quadratics that are, in the basic form, ax squared plus bx plus c is equal to 0. But sometimes we'll face equations that don't exactly look like that, where the quadratic equation is still applicable. And in those sort of cases, it always comes down to taking the equation and getting it into quadratic form first, or kind of using our normal approaches to solving like say for example a rational equation where it doesn't look exactly like it's not a quadratic obviously right now, but we could still use our normal algebraic approach to get started. Like I could use either the LCD method or cross multiply in this case. Since here I have a proportion, I can use the property of cross multiplication to get rid of the fractions. And basically once you get fractions, you might have a quadratic equation resulting. If you do, obviously when you have a quadratic equation as your entire thing that's left, you can always use the quadratic formula. So if I cross multiply here, I would have x plus 2 times x minus 2 is equal to 2x. And here, since I have a polynomial equation that is not set to 0, that's always the goal, right? If you're trying to solve more difficult types of equations, it's always helpful to clear fractions and set it to 0. So in this case, this factorization will not help me solve my equations, because really, from the original onset of the equation, I know that x could not have been 0 and x could not have been 2 because those are negated solutions because you can't divide by 0. Like if I multiply this out, it will help me set it to 0. That's what I want to do. So I would have x squared minus 4 and then equal to x. And then if I subtract the 2x to the other side, of course, writing it in the proper order of polynomials is helpful because, putting it in ABC form will help me with the quadratic formula. And now I'm at the point where I have a quadratic. And notice also this one is not factorable. So quadratic formula is really the only way to progress further, in those cases when you can't factor. So x is equal to negative b, 2 plus or minus square root of b squared, 4. Minus 4 times 1 times minus 4 is plus 16, all divided by 2a is 2. So here, the discriminant is positive, so they will be real, but it is not a perfect square. It is 20. And remember, you can't take the square root of individualized components. You have to add them together before, and that will make, of course, 20, which, as I said, is not a perfect square. But I could still reduce that by a factor of 4. I could split this as 4 times 5. The square root of 4 is 2. So this would make 2 plus or minus 4 times 5. I'll go ahead and write out all my work here. But that would leave me with 2 root 5. 2 plus or minus 2 root 5 over 2. And since it's a common denominator, I could split it back apart. 2 over 2 is 1 plus or minus. And then, so this one is just going to make 1. This one would make 2 over 2 is also 1. So 1 root 5 is just root 5. And I would get my solutions to my quadratic equation, 1 plus or minus root 5. So here I get 2 answers to this original equation. And this is a little bit harder to check because if you plug that back right in, it gives you kind of some ugly answers. But this is a point where you could always check on your calculator by substituting in for x. And I forget if I've shown you guys this before, but you can always do fractions on your calculator. If you go to alpha F1, it should open up a little menu to do a fraction. And that can make these sorts of things easier. So let's say I wanted to check 1 plus rad 5. I could type that in, 1 plus rad 5 plus 2. If I do that and I divide that by 1 plus rad 5, that's going to be the left-hand side of my equation. So the goal would be check the left-hand side, check the right-hand side, make sure they're equal. And that comes out to be about 1.61. Of course, you could simplify that by hand, by multiplying by the conjugate. But, in the case of checking on an exam, you often want to save time. So using a calculator for checking your answer is totally fine. And then the second one, I would have 2 divided by x minus 2. So that would be 2 divided by 1 plus the square root of 5 minus 2. And this would give me the right-hand side. And notice that the left-hand side and the right-hand side, when I plug back in my answer for x into the original equation, come out to be the same thing, so I can kind of check that one off. And I could do the same thing for 1 minus the square root of 5 as well. But anyways, it's a harder equation, but it's kind of like, I like to think about solving equations as like having a set of tools and knowing which tool to use in each situation. So if we have a linear equation, what do we do? Whether we have a polynomial, whether we have a rational, if we have roots within our equation or something else, it's just kind of adding a different tool to our toolbox. And let's look at one more example where we could use the quadratic formula. We often refer to these as quadratic forms, but it's an equation which might not appear to be quadratic, but is actually quadratic in its own right. So let's say I had the equation x plus 3 times the square root of x plus, let's just say 10, and set that equal to 0. So these sorts of equations often resemble a quadratic, but there's a key difference in that it's not x squared, x constant. It might have different powers on it. And in those cases, you can't always use the quadratic formula, but you can specifically if one of them is the square of the other. And notice here I have the square root of x, and over here I have x. Notice this one is the square of this. And if I kind of rewrote this in a different way, I could rewrite this as the square root of x squared. And so if I kind of think about it a little bit differently, technically it is something squared plus 3 times something plus 10 is equal to 0. So this is what we call a quadratic form, and you can use the quadratic formula here. You would be solving for the inside, or what we also often do is doing what's called U-substitution. If you let u be equal to the square root of x, then I can kind of replace it with u, and now this equation appears to be directly a quadratic with the substitution of u in for the square root of x. And I could then use the quadratic formula to solve for u, because it would always be equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a, which is 2. And I'm going to get really ugly answers here because I just picked this example totally at random. But as you can see, we could progress by simplifying those answers as we did before. And then the one difference here would be, instead of solving for x, notice that this is u that we're getting an answer for. And if I want to continue and finish solving for this, I could then progress by resubstituting in, well, what I let u be equal to, which was root x. And basically root x will be equal to all of that stuff from above. Which again, I could simplify by changing the square root of negative 31 to root 31 times I. And here I would need to square both sides to solve for x, because I have square root of x is equal to this. So basically x would be equal to this stuff squared. Very ugly answer. And again, we could simplify by doing the math, but I really wanted to focus on not the answer, because I just made up an example off the top of my head, which oftentimes real regular equations won't have pretty answers. But if you catch my drift, the idea of U-substitution and applying the quadratic formula to your equation after substituting u is kind of the key idea in this sort of case. And looking at one more quadratic form, I'll pick easier numbers for this one. Let's just say I had x to the 4th plus 3x squared plus 2 is equal to 0. And again, notice how this one's squared, x squared, and this one's x to the 4th. It's not a direct quadratic, but this one is the square of this one, and that's why we call it a quadratic form. So I could think about this as u squared plus 3u plus 2 equals 0, where u would be equal to the middle term. And what can be more helpful to remember is u is always equal to the variable on the middle term, and this one, assuming it's the square of this one, will be the proper way to convert it to its quadratic form. And then, of course, I could progress via quadratic formula, or if you can factor it, like this one's really easy to factor it, you could progress via factorization instead, u plus 2 times u plus 1. But, of course, it is a quadratic. You could use the quadratic formula if you prefer. This would give me two solutions, u is equal to negative 2 and u is equal to negative 1. And I would I could progress by taking the square root of both sides here. So again, reversing the substitution, I made up some, if I was more careful with my examples, I could have made up ones that had real solutions. But in this particular case, notice that I have x squared is equal to -2, x squared is equal to -1. And if I apply the square root property to both sides, I get plus or minus the square root of -2 and plus or minus the square root of -1. Both of these are imaginary, but we still come up with answers which in some cases we don't really consider imaginary answers as applicable. Like, say for example, these equations were modeling a parabola or this, some problem in physics or engineering. Sometimes imaginary answers are not acceptable. Like here, I'll get plus or minus I and plus or minus square root of 2i as my 4 answers to this equation. And sometimes those sorts of answers are not what we're looking for. But again, anyways, I'm not trying to focus on the answers here, and because here I didn't even with certain types of equations, like when it involves a root, sometimes, one or two of these answers may not have worked at the end of the day anyways. The main point I'm trying to focus on, and sorry, this video is getting a little bit long, is how does U-substitution work, and how do we apply quadratic formula to examples where it might not be obviously applicable from the onset.